Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is changes in internal energy, enthalpy, and entropy using equations of state, and the sections in the textbook are 12.2 to 12.3. So here are the learning outcomes. At the end of this video, you'll understand where these general differential equations come from for du, dh, and ds. And you'll also know how to use those to calculate values of delta u, delta h, and delta S using just a non-ideal equation of state. So in general, this is the question that we're attempting to answer with this video lecture. How can we calculate a value for change in internal energy, or the value for the change in enthalpy or entropy, given just an equation of state? And remember, an equation of state is an equation that describes PVT behavior. So it's an equation, and these three variables appear in it, and I want to use that to find these values for internal energy, enthalpy, and entropy. And the reason we want to do that is we don't have internal energy meters or enthalpy meters or entropy meters for that matter. And so there's no way we can't just stick a sensor into our substance and determine that. So for example, here's an equation of state you've seen before. This is a very simple one. This is the ideal gas law. Again, we've got P, V, T, and it's just very proportional to this value of R. And we saw here's how we can go ahead and find the internal energy. And in fact, that was just from the definition of CV. We defined CV as the partial derivative of du dt. And so that's where we ended up with this equation. Same thing with dH in terms of CP. And then here's one of our TDS relations. There was actually two of them, but this is one of them where we have ds, and now it's a function of changes in temperature and pressure. But we could go ahead and again find that. But all three of these were only valid for the ideal gas law. All right. So here, let's go ahead and answer this question a little further. What if we had a different equation of state? Here I have an equation which is like van der Waals equation of state, where again I've got P, V there, and T, but I've got a couple extra parameters, A and B, and those are just constants, similar to the value of R. So here's this other equation of state, and the thing is, how could I now determine delta U, delta H, and delta S? Well, it turns out what I can do, and this is what we'll see here in just a few minutes, is I can do something similar. I can have CV dt, but I'm going to have another term. And effectively, this is the temperature dependence on internal energy, but now I've got a pressure dependence. And that's the difference. Ideal gas law, there was no pressure dependence on the internal energy. But now we're going to have a pressure dependence, so we're going to need to include another term in our du equation, another term in our dh equation. And in terms of ds, I'm going to again have a temperature contribution. I'm going to have a pressure contribution, but it's going to be different than the one I had for ideal gas. And so I'm going to have a different second term right over here. And that's what we want to go ahead and determine. We're going to do that with a little bit of calculus. So let's go through this. And the important thing on the next slide here is just to kind of follow along the steps and understand where these equations originate from. All right, so first of all, I've got a simple compressible system. So that says the internal energy can be expressed as a function of two variables. And so, for example, I can express it as a function of T and V. And I can pick any two. I'm just choosing to start with T and V. And now I'm writing the total derivative for du using T and V. So I've got these two partial derivatives, du dt and du dv. So it's just a little bit of calculus. And any variable or any function is a function of two parameters I can write this way. Now, we recognize that the partial derivative of du dt at constant v is, by definition, CV. So this purple term becomes that purple term right there, just by simply the definition of what C sub v is. And now I just went ahead and brought this black term right back down. All right, now I'm going to do something similar. So I'm going to hold on to this equation for now. And again, I've got entropy now, and I'm going to again choose to express this as a function of two parameters. I'm going to use T and V again. So what I've written is just the total derivative for what ds is. Okay? All right. Now I'm going to take this TDS relation. I'm just kind of wrote it in a different form a little bit. So if we go back to chapter 7, you'll see this TDS term came from the PQ term, and this PdV term came from the del W term. With an energy balance, and that was equal to du. So there's my TDS relationship. Right? And now what I'm going to do is just go ahead and move down what these particular terms are. And so what you can see is these blue terms right over here are going to be equivalent. Because I've got T And then I'm going to go ahead and substitute in this whole, for this ds in red, I'm substituting in this ds here. So I'm substituting in all these terms on the right-hand side. So here's the t. That's this t right over here. And then this blue term is that blue term right there. All right. And then I've got the same thing coming down over here. I've got a dv. And so that's going to be this dv right over here. This term had to come down and again get multiplied by t. So I've divvied out the t times those two terms and then put them in those two places. So now I've got this equation for du that becomes that equation there. Okay. Now what we look at is we're going to compare two equations. Let's compare this equation up at the top, du, and this one right over here. These are two different equations for du arrived at different ways. And they're a function times dt and a function times dv, which means that this cv has to be equal to this term, but more importantly, this term right over here, this dv term, has to be equal to this right over here. So that's what I have written. The partial derivative of du dv at constant t has to equal this bracketed term right there. And now I'm going to do one more thing. I'm going to use the Maxwell relation. This becomes kind of handy here. And this was one of that we derived before. So there's my ds dv. I'm going to go ahead and put it in right there. I'm going to replace it with dp dt at constant v. I like that better. pt and v, those are easy things to go ahead and measure. So what this means now is that this du dv term becomes this that I have just by substituting in my Maxwell relation. And now I can go ahead and put that back up into my very first equation for du, and this is what I arrive at. du is my temperature dependence, and then here's this pressure dependence term that I'm going to go ahead and integrate through volume. And so this right over here is more or less the ideal contribution to internal energy, and I like to think of this as the non-ideal contribution to internal energy. Okay, so let's look at what we have here. I have an equation for du. I can go ahead and integrate that to go ahead and give me well, my change in internal energy. I can integrate it from u1 to u2. dt, I'm going to integrate from t1 to t2. And this whole thing right over here, I'm going to integrate from v1 to v2. So going from condition 1 to condition 2, and I'm evaluating it depending on each one of these particular parameters. Okay? So the first thing you need to do when you do this is you've got to evaluate what this term is, this non-ideal term that's in front of the dv. Okay, so for example, let's say I had this equation of state. PV equals RT. I'll start with my ideal gas equation of state. And I want to evaluate the term on the right-hand side. Okay, so the first thing I need to do is I need to take the partial derivative of pressure with temperature. So I need to express this. P is equal to, and it's going to be RT over V. I just rewrote that. And now what I want to do is I want to take the partial derivative of pressure with temperature at constant volume. If I look at that, well, the dP/dt at constant V is going to be simply R over V. Right? And so then V is constant, so it's just simply R over V. So now I can go ahead and plug that in, and my bracketed term now becomes T, and then that becomes R over V, is that partial derivative term, and then minus P. Right? Well, now if I look, P is equal to RT, so that right there is going to be equal to T R over V minus RT over V, and those right up there are the same, so I realize this whole thing is equal to 0. So therefore, du is equal to CV dt plus 0. There's no pressure dependence term. And this isn't surprising. I used the ideal gas law, which there was none. But we realize we end up with this equation using this more general form as well. Okay, now let's go ahead and do a slightly different equation of state here. So now I've got one that's non-ideal equation of state. And I'm going to do the same thing. So first thing I need to do is evaluate my partial derivative. So I need to re-express this, put P on one side. And so I'm going to say P is equal to RT. I'm going to divide by V minus B. And then I'm going to go ahead and subtract my A over V squared. So just want to explicitly solve for P. Makes it a little easier to take my partial derivative. So I now have dP dt at constant V. And so let's look at that. V is a constant, and so I'm going to end up the first term, I'm going to get an R, V minus B. And the second term is a constant. V is a constant, A is a constant. That whole thing is 0. So the only thing I'm left with in my partial derivative is this first term right there. So now let's go ahead and evaluate my bracketed term. I have T times, now I have R, V minus B. and then subtracting B. All right, and now let's go ahead and substitute in what is pressure. So that again is going to be T R V minus B, and I'm substituting in this term right over here for pressure. So minus RT V minus B, and then I've got minus, so it's going to be plus A over V squared. And now I realize those first two terms are the same, so this becomes 0, and this becomes simply A over V squared. All right, so now I can go ahead and do this integral. So I'm going to have delta U, I'm going to do my integration. And so the first term I'm integrating is c d dt, integrating from T1 to T2. And then the second term I'm evaluating the integral from V1 to V2 of A over V squared dV. And that is going to become CD, T2 minus T1 is the integral of the first term. And the second term out over here is going to be minus A, and this is going to be 1 over V2 minus 1 over V1. And you can verify that calculus if you want. And that right there is going to be my change in internal energy. All right, so here again I have a temperature component, and this one over here, which is effectively a pressure component, because that A was more or less describing pressure effects in my equation statement. So just go ahead and plug in a couple numbers and kind of get a feeling for this. And so here's the question, the example we're going to do. We're going to find the change in internal energy for carbon dioxide going from 20 to 40 degrees at a constant pressure of 5 megapascals. And we're going to go ahead and use the equation of state that we had before, which means this is now my equation for the change in internal energy. So if I look up CV for CO2 at this temperature, not a big temperature, I can change, I can assume it's about constant. That's about 0.657 kilojoules per kilogram Kelvin. That's off of the tables. And then I need a value for A. And so remember from van der Waals equation, here's my equations for A and B. You can get those out of chapter 3. And so if I go ahead and plug in my values for A, and I'll go ahead and just skip to this for you, but you can go ahead and do it on your own and determine that A has a value of 0.188. And the units on A are a little weird. They're meters cubed kilojoule per kilogram squared, but it turns out that when I take that value of A, divide it by specific volume, I'm going to end up with a specific energy term. So my units all work out like that. Okay, so let's go ahead and calculate my delta U. Just give ourselves a quantitative number. So 0.657 times my 20 degrees Kelvin that it changes. And then subtracting my value of A, 0.188. And I got kilojoules, meters cubed, those units all work out. Now I need values for V2 and V1. And what I have to do that is I come back to my equation of state, and I got to solve for V, okay, using temperature T1 and P1, and then solve for V2 using T2 and P2. P1 and P2 are the same, but I'll have different values of temperature. So if I do that, and again, I'm going to go ahead and just skip this for you, but you can verify that's going to be 1 over 0.0091, and V1 is 0.0078. And so these two terms right over here, this first term comes to about 13.14, and then I've got this number comes out to be an additional, I'm going to subtract, and this is actually a minus term of 3.46. So this comes out to about 16.6 kilojoules per kilogram. And the other important thing to see is so here's the temperature contribution, which is about 13, and then I've got about another 25% due to the pressure contribution, the non-ideality, which my value is about 16.6. So that's the way that you go ahead and evaluate changes in internal energy for non-ideal gases. So here's the equation that I had, du, my ideal term, my non-ideal term that I need to add together. And so I just want to kind of synopsize it. You can do a very similar thing and come up with an expression for the change in enthalpy. We won't go through all that. It's very similar to what we just did, and you can see the details in the textbook if you want. But again, I've got an ideal contribution and a non-ideal contribution. And this one right over here, I will integrate the second term from P1 to P2. And if I look at my ds equation, so here's that Cp dt term. And now here's the general form that I need to evaluate, ddt at constant P. And this right over here is going to be different for different equations of state, but this is, again, the pressure contribution to changes in entropy. And so that's the way I would go ahead and find my values for ES.